Alright, so welcome back to the final video for this series in Homework 2 for Transport Phenomena 1, where today we're tackling the problem of, well, we have to show that the fanning friction factor, lowercase f, is equal to 16 over the Reynolds number. Okay, and remember, Reynolds number is a dimensionless unit, so by extension, the fanning friction factor is also a dimensionless unit. Okay, and the way we're going to prove this is we're investigating a pipe. We have a pipe of length L and radius big R, okay, with fluid flowing downwards. This fluid is a Newtonian fluid, and everything is at steady state, meaning that all derivatives with respect to time is going to equal 0. Okay, that's important for not too far on. Okay, so at this point in time, we're going to start off. We're going to start off with this to prove that the fanning friction factor equals 16 over the Reynolds number. We're going to start off by taking a look at a force balance, okay? And the force balance goes like this. We first consider our pressure forces, and we realize that, hey, the pressure at position 1 and position 2, it's both atmospheric pressure, okay? So therefore, the pressure forces are both the same. What does that tell you? That tells you that there's not going to be any pressure recovery here because there's no increase in pressure down the line. Okay, what else do you know? Well, you know that there's a change in z, change in coordinate z, so change in height. So there's a maybe I don't want to go down that line of thought. Well, we'll scrap that. What else do you know? You know that for all we're interested in this particular cylindrical section that we've taken out of our pipe, and it's just a cylindrical section of fluid. Okay, and how do we do that? We know that for all objects we have mass, so we have a force of gravity directed downwards. So let's do force of gravity equals mg, right? But this force, we can express this this mass, in terms of density multiplied by the volume of our, excuse me, a phone call. We have a we know that we can express mass in terms of density multiplied by the volume of the cylindrical section that we're interested in. So let's go off and do that. So let's do 2 pi r squared multiplied by the length of the pipe, okay, is again rho g. Okay, and is this our only force? And we consider, no, it's not our only force, because let's focus on the idea of this typical velocity profile for a cylindrical pipe. It looks something like this, right? And what you notice is that for the fluid in the center, okay, for laminar flow, it's the fastest, right? And its neighbors are not so fast. And how are its neighbors gaining its velocity? Well, it's gaining it by this boundary in the middle, dragging its neighbors along. And because it's dragging it along, there needs to be an opposing force, right? And that opposing force happens to be this idea of shear stress force, okay? And we are told that it's a Newtonian fluid, so we can go off and write our Newtonian fluid definitions, so, which says that the shear stress, okay, shear stress again is in units of force per unit area. Shear stress is equal to the viscosity multiplied by shear rate, where the shear rate is the derivative of the velocity with respect to a coordinate in the perpendicular direction. So that's r. Okay, so in other words, equals mu dv dr, right? So we have shear stress. Now, how about the force? I had hinted at the fact that the shear stress is in units of force per unit area. So the force is going to be generated by the area of the area of the surface. The liquids are in contact with one another. So this we're going to take a look at this liquid here, and the liquid directly neighboring it, right outside of our cylindrical subsection. And that's being dragged along, so there should be a force counteracting it, right? And that's happening for all along all along the surface of the cylindrical section that we've defined. In other words, the force, we say that the shear force is equal to mu dv dr multiplied by the surface area of the cylinder minus the top and bottom, which is 2 pi r multiplied by L. Okay. And now we take a look at our force balance, where the force, all forces, is equal to 0. Okay, we can say that because we know that we are at steady state and F equals ma, right? Where a is the second derivative of position with respect to time. And that is the derivative with respect to time. For a steady state, all derivatives with respect to time equals 0. So we say that our forces are in equilibrium. Okay, so 0. 0 equals rho 2 pi r squared, length of the pipe, plus g, plus mu dv dr 2 pi r L. Okay, so at this point in time, we would like to find a velocity profile for this pipe. So we would like to solve for dv dr and then integrate, right? So let's go ahead and do that. We say that dv dr is equal to negative rho 2 pi r squared L g over mu 2 pi r L. Okay. I just realized something. Where did this 2 come from? This doesn't seem right. The let me review. The should be equal to pi r squared. Yeah, because that's the volume. Right. I had accidentally included a 2 there. I knew something seemed off. Okay, so now we say something's canceled, right? We got that. So now we have dv dr equals negative rho r squared g over mu. Let's put the 2 in the front. 2 r. So, oh, I nearly forgot. The r's do that. Okay. Are we all good here? Okay. So now we go off and integrate, right? If we integrate this with respect to dr, same with here. Let's do in this case, you typically see this as a separable differential equation, but in this case, we don't want to do that. Okay. So we go off and integrate it, and we're left with v is equal to negative rho g over 2 mu, rho g over 2 mu, multiplied by r squared over 2 plus c, right? And we have v negative rho g over 2 mu. I was trying to combine the constants. 4 mu r squared. Okay, so, plus c. So now it comes to the question of what is that c? Well, we can just so happen to use the principle of the no-slip boundary condition, which states that for a liquid against a solid surface, so we have liquid here, right? The liquid directly adjacent to that stationary surface, directly adjacent to it, is the velocity of that is 0, okay? And for our pipe, the surface of the pipe is 0. The velocity should equal 0. In other words, when the radius equals big R, radius of the pipe, velocity equals 0. And guess what? We have an expression right there for that. So we go off and say that 0 equals rho g to 4 mu multiplied by big R squared plus C. Okay? In other words, we have an expression for C, like so. C equals positive rho g over 4 mu, mu being the viscosity of the liquid, big R squared. So now we have the V is equal to negative rho g over 4 viscosity, little r squared, plus, well, rather, we can factor it all out. We can actually factor it all out and say that it's going to equal to the constant rho g over 4 mu, big R squared minus little r squared. Okay, and that's our velocity profile. Okay, I went ahead and moved us to a new page since we ran out of room, but let's quickly remind ourselves of the goal here, at least the temporary goal. The temporary goal here is to try and find a expression for volumetric flow rate. Okay, and it looks something like this. Volumetric flow rate is equal to the velocity multiplied by area, but the area is not constant. The area is changing, so we say it's differential area. This differential area is going to be this infinitesimal difference between a cylinder inside of the pipe and a slightly bigger cylinder, okay? And from a top-down perspective, this is the area, okay? And that's all zoomed in. And in essence, this is a rectangle. This is a rectangle of width dr and length 2 pi r, right? And let's go ahead and plug in that V in there. So we have Q is equal to, that 2 cancels out, rho G over 2 mu pi r squared, r. Go ahead and distribute our r. Okay, actually, let's go ahead and wiggle that out. Okay, and this then becomes an integral, and we have to ask ourselves, what are the bounds of integration? Well, for our analysis, we're varying the size of the cylinder, right, from 0 to the edge of the pipe, so big R. Therefore, the bounds of integration is from 0 to big R. Okay, so let's go off and do this integral really quickly, and it looks something like this. If you distribute it through, don't forget the dr, distribute it through, we have r squared r minus r cubed dr. Okay, so then it looks like big R squared over 2 minus r cubed over 2, evaluated from 0 to big R. Evaluate that becomes r to the cubed over 2 minus big R. I said cubed, I meant to say to the 4th, over, that was a mistake. This is a mistake. Should be 4. Okay, and this equals r to the 4th over 4. Okay? So if we plug that back in, we have Q, volumetric flow rate, is equal to rho G pi over 2 times 4 is 8 mu big R. Okay, so that's our expression for volumetric flow rate. This looks good, looks really good. Okay, let's not lose heart and keep moving on. So we then go off to the next page, and I have this here already because this is from our textbook. Okay, it's the expression for frictional heating in terms of what? Fanning friction factor. Isn't that the whole point of what we're doing? The end is in sight. So we, what do you notice about fanning friction factor? You notice that it's in terms of d diameter, right? D diameter, And we have this 4 and this 2 here, and you might be tempted to go off and simplify that. And true, there's nothing wrong with doing that, but the motive behind expressing frictional heating like this is that this is extremely similar to our velocity term in the Bernoulli's equation, right? That's why it's being represented that way. So the point being is that this is diameter and this is radius. So we would like to turn this into diameter because the pathway to do that is extremely easy, and this will open up pathways for potential simplification. Okay, so that's the motive behind turning big R to radius. And you know that big R is radius is half a diameter, right? So rather, a radius is half a diameter. That's right. So d. I totally forgot a 4 to the 4th power. I evaluated correctly. I just had a copying error. There we go. Don't forget the to the 4th power, because we have d to the 4th over 2 to the 4th. Okay, and d to the 4th over what do you call 16, right? So then Q is therefore equal to rho G pi 8 times 16 is 128 mu R to the 4th. Okay, looks good. Good. Oh, not good. Should be D. I need to control myself when it comes to copying errors. Okay, so now we go off and we introduce another tool in our toolkit, that being Bernoulli's equation. Okay, and we have the pressure term, right, over rho, and the velocity term, right, over 2, and the change in altitude term is equal to negative frictional heating. Okay, oh, I'm getting better at drawing those Fs. I like that. And we take a look at this and recall that at the beginning of the problem I had mentioned that the pressure at the top and the bottom is both atmospheric pressure. Therefore, there's no pressure recovery. Therefore, the pressure term is 0. There is also no change in velocity, right? And this change in altitude, right? This change in altitude for our pipe, we're going from position 1 to position 2, and we're traveling the length of the pipe we're interested in. Therefore, the delta Z, the change in altitude, is equal to negative L. Okay? G equals negative frictional heating. Okay? And the negatives cancel out, become little positives. Okay? And you might take a look at this and think, hey, what's going on? How do we relate all of this? So look at this jumble here. So let's highlight our equations of interest. These are our current equations of interest. Look at this jumble. Okay? But you notice, hey, I got G here. I got G over there. That looks like a pathway to me. So we go ahead and pursue it. Okay? So we say Q is equal to, G. I said G and I wrote Q. G is equal to Q 128 Q mu over rho pi d to the 4th. Okay, so you can plug that in and we get L 128 Q times mu over rho pi d to the 4th equals the frictional heating factor, which is equal to that expression up there. So we have 2 fanning friction factor over L over D multiplied by velocity. Almost done. We're really close. Okay, so let's do some canceling. See that L cancels out, right? This D makes that a 3, and 128 divided by 2 is, I don't know that off the top of my head. It is 64. I should have known that. Okay, so let's go off and see what we can do here. 64 Q mu over rho pi d cubed equals fanning friction factor multiplied by v, right? I can bring the v to the other side, like so. And let's not lose heart. Doesn't look quite like our goal, right? Our goal is 16 over the Reynolds number. So what does that tell us? That tells us A, we're gonna find the Reynolds number somewhere in here, and B, we still have this Q here, okay? This Q can be expanded, right? Recall that. This Q can be expanded. Because recall that Q is equal to actually, maybe I don't want to go all the way back. Q is equal to this, right? I am a little unsure of what pathway to take here. Q is equal to, see if I write down, we'll remember. Q is equal to oh, I see. That's why I got confused. Q, we want to take a look at Q in terms of diameter now. Okay, so Q is equal to what? Is equal to 2 pi r, or actually just pi r squared multiplied by velocity, right? And in terms of diameter, that's Q is equal to pi d squared over 4 multiplied by velocity. And if you plug Q in there, right? If you plug Q in there, we have 64 divided by 4 is, hey, 16. F is equal to 16, right? Our velocities cancel out. And this d gets simplified, and our pi's cancel out. Okay, so we have 16 mu over rho d. Okay, am I missing a term? I don't believe I am. Okay, and you see we're super close here. And if you go off and check out what the expression for Reynolds number is, okay, the expression for Reynolds number says that it's rho vd, all right, and rho vd over mu. So what I'm taking a look at here now is I'm missing a v where I'm not supposed to be missing a v. Oh, I see. It was a copying error. V squared. So that v gets canceled and v remains in the denominator. Okay, we almost lost heart. But check this out. That's the reciprocal Reynolds number. So now it's 16 over the Reynolds number. Bang. We are all done. And this is the three-page derivation of showing, hey, the fanning friction factor equals 6. Oh, I had that still up. This is the 3-page derivation for, hey, the fanning friction factor is equal to 16 over the Reynolds number. All right, and this will conclude the series of videos for homework 2 for transfer phenomena 1.